Welcome to Flat Earth Debate. I'm your host, Nathan Oakley, and if you are new to this channel, or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. If you would like to support this channel, there is a super chat that runs alongside each of these shows while they're live, and a link in the info box below this video once the video has rendered. But most importantly, if you would like to join the discussion, simply mute the page you are currently watching, then click the link in the info box below this video to join the panel and express your views on the shape of the Earth. There are a couple of rules. Number one, please don't swear. If you do, you'll be ejected, and if you are, please don't try to rejoin the stream using sock accounts. You'll be warmly welcome back on the next stream. Please also share the show, as this increases the live audience, of course, and that in turn increases the chances of a more diverse panel. So please share the show. And one last time, if you are new to the channel or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. Now we are joined by Ranty. How you doing, Ranty? Good to have you.
Good evening. Glad to be here.
Thanks for being here. Nice to have you. What do you know?
I was just over in Anthony's first live stream that he's done in a while, actually. We had Dawn over there. I think he got a bit humiliated, really. I think he rage quit at one point.
Yeah, he
was holding his toes to the fire.
selective acceptance of certain facts, does he not?
He does. Yeah, he's not a very good debater, to be fair, so it wasn't a surprise that he couldn't handle ISA.
Yeah, he's got good taste in drum and bass, though.
Yeah, I mean, I think him and ISA could actually make a record or some kind of music together for sure, but whether or not they'd get along, I don't know.
Maybe.
Being on the opposite side of the fence. So how's your day been?
Been all right.
Bit late for me doing this.
Yeah, went to see the mother-in-law. You know how it is. Didn't see her last week for Mothering Sunday. Hey, Arwen, how are you doing?
Hey.
Good to have
Hello.
you.
Good evening.
So yeah, it's been a nice day. Clocks went forward.
Yeah,
Lovely long day.
Sun's been out.
Yeah.
And been quite warm around here.
Hey, Timothy Osman, how you doing?
That was
really
a
you?
proper spring day.
How's things with you, Arwen?
That was great. It was really nice weather. As I said, it's a proper spring day. So, all's good.
Yeah. There was snow on the ground 3 or 4 days ago whenever I last went to my grandmother's house. And in Birmingham, there's still snow. So 4 days later, it seems like winter was never here. You know, it's a lovely day today. Not very flat earthy, but there we go.
No, but I was talking to Anthony before, and you know that guy that's done the observations from Belfast, looking towards
light on here or something?
Yeah,
hello?
Yeah, we hear you. Sorry, I kicked you because I couldn't hear you say hello. Didn't know if it was a sock.
Oh, that was like 2 seconds. Okay, cool.
Good to have you, Tim. So, what are you saying, Ranty?
Yeah, so the guy from Belfast, he said it was a beautiful, clear day today, and he was actually getting some really good observations done of the Isle of Man.
Cool.
So hopefully you should have a video up in the next day or two. Fingers crossed.
Hello,
Ruhif, hello.
Is that really you?
Hello?
Hello,
Hello.
Ruhif. You say a bit... Yeah, I didn't think it was him, not at this time of day. He's probably asleep.
It's the same guy that does the same music every time. It's quite amusing, actually.
Yeah.
Yeah, what song is that?
I don't know.
I'm not sure, but he'll be back again. He normally comes on about 4 or 5 different ones, doesn't he? Right, shout out to Ute, hello. And Base, hello. Daylight, Ohio, hello. John Watson, hi.
Is there a... I'm sure one of the trolls showed me a video
So I called
of,
this I called this a while ago. Kind of noticed how basically, you know, Ranty and Riley, their observations clearly show obstruction, and evidence like the stars, moon, and the sun for the spherical Earth are completely disregarded as intangible or some kind of hologram. Basically, any kind of observation on the ground. One moment, I haven't finished. Basically anything on the ground is now just some kind of a refraction. So, question really is like, where do we go from here? What kind of evidence is going to prove anything to you guys?
A cumulative drop into the distance, Tim. That's what's going to prove it. So, where's your proof?
So, a cumulative, is that a cumulative drop?
Cumulative, yes. Cumulative drop into the distance. That would
let me look up that
be
word.
Required for curvature.
Cumulative.
Yeah.
So yeah,
sorry,
obviously,
I'm Dutch. I have an accent. Sorry.
Obviously, we have many videos, evidence of a cumulative drop with obstruction being the case. So, really, you just say it's some kind of atmospheric disturbance or whatever. So I'm just saying, like, there's absolutely no.
You get misty in that evidence of yours. It's really barely visible at all. So
again, the question was, what kind of evidence could be actually provided to you guys? Because you dismiss everything in the sky.
No,
you dismiss the spherical model. I wasn't talking.
With
Go ahead.
actual non-misty far view, and then your cumulative drop. So cumulative or whatever you want to call it.
A cumulative drop on a clear day. On a clear day.
Cumulative drop on a clear day would convince you guys that the Earth is round or curved in some way.
It would start to prove there might be some viability to the curvature theory.
So you're saying that all of the evidence from Soundly, all of the evidence from Ranty, and everybody is... Oh, I was almost done with my sentence. All of that is misty days? All of it?
Yeah, it's just fog, bro.
Yeah.
What's that, Nate?
It's just fog.
The fog of flat Earth, I agree. Yeah, it screws up your mentality.
You know the salt lakes.
It's the fog that proves your ball. That's what it is.
What about the salt lakes?
So we have different areas of Earth that are incredibly flat, including the salt lakes.
Tim's going.
I was actually going to go to the. It's called the. I live in Utah, so I'm actually about 30 miles probably from the Great Salt Lake.
Hi, Dawn.
And
right.
Hello, it's me.
Hey, Dawn. Hey, is that you, Arif?
Just chill. Sorry.
Is that you, Arif?
Hey.
Yeah, it is. Okay, can you tell me both? Sorry, carry on, Tim and Ranty. You're talking about salt.
So anyway, yeah, the salt flats in Utah. I was actually going to go today with my P900, but it's kind of crappy weather. But so you're saying that salt flats are completely flat?
Well, seeing as they're measured as
they're
flat,
not salt curved.
Yeah, they're not salt.
They're measured as salt flats.
I just wonder how they
withstood
the force of gravity and stayed flat, whereas gravity should be curving everything into a ball.
What evidence do you have that they're completely flat in the terms of flat, like a piece of paper laying down on something flat? What evidence do you have of that?
It's measured. Let me get a link up for you. 1 minute.
Okay, because it's kind of like the same thing as Kansas being flat, or I wasn't talking like Oklahoma being flat and stuff like that. It's actually level, and level on a sphere basically entails level in accordance with the center of the Earth, so the core of the Earth. So level and flat are two different words, and they don't mean the same thing.
Okay.
Share my screen. I want to show him the problem, the contradiction that people are kind of having with this. Y'all can see my screen?
Oh gosh, not paint again, dude.
You're going to love it. So here we have a boat. Right here, right? It disappears in the distance over, I guess, what you'd say the supposed curvature. Okay, fine. So it disappears behind this curve, right? In the forward direction, it's only so far. But left to right this way, it's 3 times the distance. So basically left to right, we should see enough curve to cover up this 50, 20, 30, 40-foot boat. Why isn't this seen on the horizon? Why don't we see a curve that should compensate and cover up this boat this much? Why do we tend to see something like, oh, this? Just a flat, level horizon. And not only that, a boat that comes back into view with a powerful enough telescope. We see no hump obscuring the boat at all. Why is that?
Nathan, do you believe that a powerful telescope will bring back an obstructed boat on the ocean?
Obstructed boat? That's very carefully phrased.
Do you believe that? Because that's what he's saying. He's got like Eric Dubé 1.0 proofs in his head. So I'm just wondering, do you believe that?
So if I was to lay it out for a new audience member who was absolutely new to Flat Earth, I would say that you could stand on the beach. Oh, got beyond the imaginary curve without a camera. Definitely a troll. So you stand on the beach and you watch the boat go over the horizon. Then you pick up your 2x optical zoom camera and you bring it back into view. And then, with your 2x optical zoom camera, you watch the boat go over the horizon. And then you pick up your P900 camera and you bring it back into view. And then it goes over the horizon on a clear day. And then you pick up your binoculars and you can bring it back into view. Now, at no stage during that explanation does it get obstructed by anything other than perspective, i.e. it goes out of your field of view of the camera. But on a day with plenty of refraction effects, or if you're really close to the beach with your feet in the water, there's a good chance that you will have obstruction, formerly known as curvature, block the boat. But as Ranty has demonstrated, you can go up a few feet higher and bring it back into view. Literally a few feet.
All right, so there's a lot of things wrong with that and some things right with that. Obviously, elevation on the spherical model will bring things back, so to speak, and that's kind of what Soundly shows with that drone that he can zoom in. As far as bringing the boat back completely, I really thought that you would know better than that, Nathan. When it's obstructed, or let's just say with your eyes, and it starts to get really small because of perspective, and you bring out a zoom lens. Okay, yeah, you can see most of the boat, but when things are obstructed, it doesn't matter if you get your P900 out and then a telescope out. You can't bring the obstructed back, and that wouldn't even be the case on a flat Earth either.
Yeah, I agree. I mean,
So
once things are obstructed by the atmosphere, or by the zone of invisibility, as Arwin calls it, was credited to some paper by some high school kids out in China. But there's a zone that you physically cannot see past, depending on how low you are. And as I say, you just go up a few feet higher, apply the same maths, and it doesn't get obstructed because you don't have those effects if you're a little bit higher. I'm not talking up in the sky, I'm talking a matter of feet.
Yeah, and this is why you guys seem to want to go and take the highest observation points, elevation points with your observations. And really, I've made the point before, if you're going to try to...
Hold on, Flat Earth
Go ahead and
Pirate,
talk,
can you hear
person.
us? Hello? Can you say hello? No.
I doubt that. Kick that. Anyway, if you're trying to map the flat Earth, you would take it from all types of elevation. You wouldn't go to the highest elevation and say, hey, look, we have a map and model of the flat Earth. I think that's probably the height of your intellectual dishonesty. Just saying,
that is yours.
Nathan. I was talking
you are
about Nathan.
dishonest in suggesting that we do that because we, well, me not personally, but I know Ranty has taken plenty of beach level photography into the.
Where is that,
distance.
Ranty? Do you have some of that?
I do, yeah.
Of the Isle of Man?
Not of the Isle of Man, no.
Okay. What can you see the Isle of Man from the ground?
Yeah.
But not all of it, as much as you see when you're high up?
No, you see more when you're higher up.
Okay. Well, this kind of goes to the point of what Arave was just showing with the just completely out of scale, bizarre drawing that he just made with boats going over the horizon. And furthermore, the x-axis argument is a tired argument. It's been gone through ad nauseum many, many times.
Like the
so I really
proved in that they reproved with Sagnac. Maybe we need Heck, might have made a couple mistakes in some of these observations. Just saying.
What Sagnac? What Sagnac experiment are you talking about in this
He
reference?
bounced a bunch of light rays off of mirrors and basically said if the ether doesn't exist, it's not going to be slowed down by these ether particles in the atmosphere or whatever. And he found that they were slowed down. That when he shot a beam of light against quote unquote the ether and with the ether, they came back to the same mirror plate at different times, meaning the one that was going against the ether was obstructed and slowed down by something in the atmosphere. So it's like it going back and forth. You got Einstein saying there's no ether. Then Sagnac does this experiment that actually points to an ether. So, how much of the stuff do we need to reanalyze? And maybe we were wrong about the ether and other things too, and maybe this round Earth thing.
You're talking about the luminiferous ether, and you're talking about Aries failure, basically at the same time.
Yeah, it seems like it just got jocked by gravitational theory, and they talk about gravitational fields. Maybe it's an ether field, and gravitational fields still part of the main components of ether field theory. Kind of feels like you have a gravitational field and a magnetic field, which are two parts of one unified, elegant ether theory.
Well, it's nice that you say maybe. So,
I mean,
we were talking about things that are evident in people's evidence and stuff like that. So,
no,
maybe
no. We're talking about concepts here, Tim. You confessed to this yesterday. So to say now that these things are evident, nah, they're not. These are your concepts. Yesterday, I thanked you for admitting that.
No, I was actually talking about Ranty's evidence in this context, actually, just a moment ago. But we can always go back to the Matrix Decode, his last video, the Flat Earther, for quite a while, who actually found the curve. Now, when we say that boats don't go over the horizon and we can bring them back with the P900, this video seems to kind of refute that in a lot of ways. And things like the Chicago skyline, you can't just take a P900 out there and bring back the whole Chicago skyline as if what you guys are proposing, basically. That optics, it's all optical. You can just zoom things back in once they're obstructed. It's total nonsense.
No, not all of
it. You're inserting this word obstructed. Once things are obstructed, i.e. there is a genuine atmospheric obstruction in the way, then no, you can't bring them back. But that is atmospheric obstruction, as opposed to curvature. So to say, once things are obstructed, you can't bring them back, well, that's very different saying once things go over the curve, isn't it? And we would assert there is no curve for them to go over.
Let's hold you to the same standard. So what using the scientific method do you have for what you just said about atmospheric obstruction?
Well, unfortunately, we don't have science on our side, Tim. The consensus is that it's a globe and boats do go over.
So you're just
curve.
asserting it, Nate?
Unfortunately, as I've just stated, we don't have science on our side. You have 2,000 years, however, of science to come up with scientific proof of Earth curvature. I don't. I've only been doing this for a couple of years and I make YouTube videos. So when I ask for all of science, the entire body, to provide me with proof of Earth curvature, there is a simple fact that goes along with that. The entire body of science is dedicated to this cause, and they've had 2,000 years to come up with some evidence, and they haven't got any. So if you're asking me, a non-scientist, to provide you with scientific proof of flat Earth, I'm a YouTuber. However, there are scientists, Tim, and they are absolutely dedicated to your cause of globe proof, and they have no scientific proof of Earth curve. So you want to challenge me after 3 years? I'm not a scientist, mate. Go and ask your scientist, the one that is absolutely being paid to come up with scientific proof of Earth curvature, why he hasn't got any, as opposed to levelling at a YouTuber's door, because that seems kind of pathetic, really. Why would you ask a YouTuber for scientific proof of a flat Earth when
you're asking Pete Layman on your show?
It's an alternative reality that you're pushing. You need to prove it, don't you?
Oh, right. What I'm saying is, why isn't there any proof of Earth curve when you've had 2,000 years and the entire scientific community
let me break this down. Let me break this down really quickly. I did want to talk about this.
Oh, well, you brought it up.
I did want to talk about this.
You brought it up. You just asked me for my scientific proof. You asked a YouTuber, not a scientist, for his scientific proof.
You ask laymen all the time on YouTube for scientific
what can they reference?
Stuff,
I'm not asking them to do it. They ask me to go out and do tests. And I'm saying no. I'm not asking you to go and ask me to do anything. I'm saying in 2,000 years, what has the entire scientific community, who apparently have known and understood the fact that we live on a globe, what have they come up with that you can reference? And the answer is nothing.
You're conflating two different things right now. You're conflating two different things. Your whole thing is give me proof using the scientific method of Earth's curvature.
That's correct. Why would it be unreasonable to ask for the scientists who are on this wavelength? They're on this tip, right? This tip of globe belief. They think they live on a globe. So when I ask people who are scientists to provide their proof, it should be out there and easily referenced by any layman. I'm not asking any layman to perform any tests. I'm not asking any layman to provide me with their scientific proof of Earth curvature. I'm saying in 2,000 years of globe understanding, you have had the entire scientific community who are being paid to prove this. And what have they got? Nothing. Zero.
Nothing
No
to your
scientific
standards,
proof of
Nathan.
Earth
Nothing
curvature.
to your standards.
None.
And furthermore, who does
Nothing
a scientific
we cannot
test
disprove
for Earth's curvature?
Overthought, how you doing? Can you hear us?
Yeah, blue Tim.
Good to have you. What can we do you
He
for?
said hello.
Yeah, bye-bye.
You know what you're asking is unreasonable, and that's why you semantically and rhetorically ask
Really?
this
Is it
question.
unreasonable?
So, I will ask it right here, right now. It is in absolutely no way whatsoever unreasonable to ask the entire scientific community, who are all in agreement that you live on a sphere, to provide scientific proof of Earth curvature. They're being paid for it, and they've had 2,000 years to do it. That is not
who is
in
being
any
paid
way
for that
unreasonable to ask
specifically,
for.
Nath? Answer that question. Who is being paid specifically for Earth's curvature scientific proof? Please tell me.
Scientists are of the opinion that they live on a sphere, and everything they do is based on that fact. The sphere in space is their starting point for their reality. Therefore, in 2,000 years, it is not unreasonable to assume you guys, the layman's, who believe this stuff, could cite at least one scientific proof of Earth curvature, and you can't, because there isn't
So
any.
again, you're skirting away from my actual question. You're saying there's scientists that are dedicated to proving Earth's curvature. What scientist is doing that?
No, I said there are scientists who have their base understanding on the fact that you live on a sphere. That is their base understanding. It is their starting point. So therefore, if that is their starting point, there should be some evidence that you, me, or anybody else can easily go out and acquire that is of Earth curvature. There should be, but is not, any in 2,000 years of globe understanding, and the entire scientific community being of that understanding.
What you're asking is unreasonable, and I think you know it.
I don't think it's in any way reasonable to ask for scientific proof of Earth curvature, given that you have the entire body of science under the understanding that they live on a sphere, and you have had 2,000 years to acquire it. I don't see that in any way as being unreasonable.
Proof of curvature do you want, Nathan?
Something that adheres to
There
the
is
scientific method.
He knows there is no scientifically method valid
what type?
test
He
to
knows
do
there's
this.
many types. He knows there's like endless evidence. What type?
No,
do you
no,
want?
no, 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 no. He's asking something
Maybe
very
there's a good
specific.
reason to that, Tim.
Curvature.
Maybe because
laser
there
across
is
the-
none.
That's
Maybe
right,
because
Tim.
it's not a globe.
Sticks in the water
Have you ever
or
considered
what?
that?
Apparently it's unreasonable to want scientific proof of Earth curvature. That's asking
What
too
type
much.
do you want?
No, you need. How about scientific proof
Picture
that the
of a
Earth is a
cumulative
sphere? How about
not
that?
into the distance.
Not Earth's
that
curvature,
would be
dude.
proof. And not
It's like people. It's like people asking Google
Same
how
thing.
much. What is the Earth's curvature? It's like before flat Earth, nobody even did that. Nobody even questioned these
the
things.
sky.
Yeah,
and,
exactly.
Like,
That's
tell
the
people
whole
off
point.
because they're not.
It's a belief, and we didn't
not
question
doing
it. And now
Yeah,
flat
Yeah,
Earth
well,
is
flat Earth
trying
is a
to
belief too.
question
So
your
stop being a
religion.
hypocrite. Stop being a hypocrite. You're
Because
religious to
flat
the flat
Earth
Earth. I
people
can say the
started
same
to
thing right back
question
at
your
you, you
religion,
hypocrite.
Tim. That's what that is.
Flat Earth is your fantastical religion then.
No,
So what,
it's
dude?
our
I don't
feat
say that
of
to you. I don't need
exploration.
to.
We're actually trying to figure things out instead of by
No, you don't
default
figure things out. You
believing
just
everything
assert
that we are
things.
being told by
You just assert
scientific
things
institutes
over
and the
and over
government.
and over again.
That's what
it's
that
optics. It's optics. Yeah, that's.
Yeah, you assert things over and over again. It's a sphere. It's a sphere. Asserting things over and over again doesn't make them real, and we're debunking your assertions in regards to it being a sphere.
You have not debunked anything about the spherical Earth.
Okay,
To
Nathan,
this day, you
Yeah.
have not.
Absolutely.
You're not in denial, Tim. Not at
Yeah,
all.
we aren't of the opinion that it is acceptable to measure mirages. You brought this up earlier, Tim, saying that when it comes to the stars, you guys want to make out like they're holograms. When it comes to things that are tangible, the globers want to make out like we can't touch this stuff, like it's a bloody ghost in the distance that we can suddenly start putting crosshairs on and doing mathematical equations to. It's complete nonsense. You guys tell us off for not knowing what the stars are and saying, oh yeah, it could be a hologram. Yeah, it could be. Yeah, we don't know. But we do know what Morgord Lighthouse is, yet you guys want to make out like it's a bloody ghost.
No, I never said that. That's a.
Yeah, you do. We've had this conversation. We established whether or not the lighthouse was, in quotes, there, Tim, and I assure you, on your model, it is not there. It's an apparition. It's a hologram. It's a ghost. It's a mirage. It's looming. It's all this nonsense that you want to inject to get around the awkward detail that it's not really there, mate, on your model. You can't see it. It's obscured, as you like to use that word. Obscured by Earth curve.
Geometrically, it doesn't make sense. Could I share my screen another time showing another geometrical
No, Ranty was going to show something of substance. Okay, seriously, dude.
All right,
You're a noob, dude.
because sometimes it's a
Ranty.
conceptual difficulty because you're not quite putting the pieces together
Hi,
in your
Eric.
head in a
How you
geometric
doing?
way. It could be that.
Oh, here comes the trolls.
Oh, that was fun.
Okay, go ahead,
We
Ranty.
got a whole
Sorry,
series
Ranty,
of
you're up.
bots
You
lined
presented, mate.
sorry?
You presented.
Go ahead,
Oh,
Ranty.
I'm presented, right. Brilliant, right, okay. This is a question for Tim. Okay, so here we have, this is a composite that I put together whilst I was standing on the beach at St. Bede's. I'm not really interested in the high points, but what I am interested in is this location up here. Because where my cursor is now is where I took an image of a boat. And then I scrambled down the hill and I took another image of the boat around about here. And then I got down onto the beach and I took another series of images and I walked right out. And so I walked right out to the water's edge and I took another image of the boat. So if I'm taking an image from up here, and let's give it an altitude of about 40 feet in comparison to the tide that was fully out, to about half a foot when I took the last image. And I'll show you the images that I captured. This was the boat sitting on the horizon from around about 40 feet. And then as I lowered my elevation and the boat's traveling to the left, you know, this is the part that drives it sort of thing. So as I lower my elevation, you can still see that it's on the horizon, right? How is that possible? And how is it possible when I come right down to the last image at half a foot that I'm still seeing the masts the same height on the horizon in comparison to the horizon as the first image, right? If I go back to the very first image, you'll see that the height of the masts are in the same position and the boat is still appearing to be sitting on the horizon. And yet the boat
can we agree that there is some miraging effects and mirroring going on in that picture? Those pictures?
Absolutely.
Can you agree that this band of sky is not Earth curve that's blocking it?
Well, the bottom of the ship is gone, so what is blocking it? The water seems to be obstructing it. So what is blocking it?
Just walk down the beach.
Sorry,
do you want to explain it again, Ranty? Explain what you've done again.
Right, the bottom of the boat is hidden due to the refractive layer on the horizon. And yet, we can measure the height of the boat above above the water by the masts and this part of the boat here, this red part that isn't being refracted right now. So if we go across to the very start, you'll see that this part of the boat, the red part here, and the masts are exactly in the same position.
But what are you trying to say,
feet.
Danny? Oh, we can see refraction, so it must be flat.
No, well, when I was
no,
above,
no, Dawn. What we're saying is what we're doing, Dawn, is actually evidencing what mirage artifacts can be demonstrated as you go up 40 feet in elevation and then down 40 feet in elevation and look at the same thing.
That's globe science showing how refraction works.
No, you've been conditioned to think this is globe science. It isn't. Unless you are about to tell me that this... Hold on, Dawn. Let me just get to the end of my sentence. Are you telling us that this obvious inverted mirage is the curve of the Earth blocking the ship?
No, I'm not.
Right, well, what the hell what are you talking about then? You've just told me it's globe science. You're going to piss me off real quick. What the hell are you talking about? This is globe science. There's no Earth curve blocking the ship, dickhead. So what are you talking about?
I'm not saying the curve's blocking it. I'm saying all you're presenting is refraction. Doesn't mean...
that I want to bring up. It's that at the horizon, this boat on the horizon from 40 feet would have been around 10 miles away. Yeah. And then within 4 minutes, when I walked down to the very front of the water and I took this image, I was at half a foot in height. No, actually about a foot in height because I got right down on my belly and took this image. Right. So here we go. Why is this on the horizon too? Why are we still seeing it? If it's on the horizon at 40 feet and 10 miles away, how can I still see it when I'm down to this low?
And also, if it was curving away on a globe, which was what I was going to try to illustrate with, you know, my, you know, extensive artistic skills, is that it would also angle away. And so the prow should be angled away at some sort of angle on this curve, because when stuff curves away from you, it also angles away from you, but it still seems to point straight up. So it's all these contradictions in this rounder,
Oh my god, dude, you're such a noob, bro. Seriously.
I know it's hard to break your paradigm, but you know, just try, you know, considering.
Listen. Let me just fill you in on this, okay? Let me fill you in on this really quickly. 70 miles on the globe is 1 degree. Okay.
Hey, Jared.
So things 70 miles away are tilting 1 degree in the other direction. Okay. Do you think you can detect a 1 degree change away from you from 70 miles?
Yes, we have cameras with an angular resolution that are easily capable of demonstrating
1 degree curvature away from you. Really?
Yeah, we can demonstrate
out of 360 degrees, 1 degree.
Yeah. Yes, we can demonstrate this with the angular resolution of a P900. You should be able to detect curvature on the axis. This is where we started. The left to right.
No, I didn't say curvature. I said, oh my god, dude. He's talking about it angling away from you, dude. Like Eric Dubay 1.0 stuff.
Is 1 degree of curvature.
Is this going to be answering this question?
1 degree of curvature, correct?
No.
Is this going to be answering this question?
What do you mean, oh my god? 1 degree meaning 1 degree of curvature, correct?
This RAF guy is just terrible.
No, he's not. He's just made a really valid point. This stuff should tip away from you, and it doesn't. None of the buildings do it. Nothing does it.
Hello?
It does.
Well,
1 degree of tilt.
Yeah, stuff should tilt away from you.
You can tell.
So this is not flat Earth evidence. I don't know why you have this on the screen.
You're insane.
Well,
I'm not insane. That's how ball works.
I'm asking it right. Well, first and foremost, right, the horizon at 40 feet should be 10
You always show obstruction, Randy, in every part of your evidence.
Just let me
That's
finish,
what happens,
right?
Dawn. Things get
Now,
obstructed.
this boat, I can see at about a foot in elevation, right? 1 foot. So the horizon to my eye line from 1 foot in elevation should be, what, around about 1.5 miles away? So how can I still see this on the horizon at 1.5 miles away when just about 3 or 4 minutes before I saw this same boat on the horizon from 40 feet that should have been 10 miles away? How is that possible on a ball? If this is sitting on the horizon at 10 miles, and then I run down to the water's edge and I see this boat and I take this image, how am I still seeing it? Why hasn't it gone behind the curve? Why are we still seeing this part of the boat and this part of the boat? And why are
So
the
10
masses
miles,
the same
a boat
height?
should be, that height should be completely over the curve of the Earth. Is that what you're saying?
Well, if it's
We don't know
it's
how
on the
far away the
horizon,
boat actually is, right?
if this boat is on the horizon now,
Well,
from 40 feet, right? Then how come it's consistently on the horizon on every single image?
You're proving obstruction and the Earth's curvature.
what's
Obstruction.
causing the
Yeah, he's
obstruction?
proving obstruction.
It's quite
He's not
amazing.
proving curvature, though, is he?
From a
Not
low
curvature.
vantage
know what
point.
to say.
Right. Is that obstructed?
There's
This
no
point?
Earth curve blocking this boat, right? You see where the sky is that's blocking it? The thing that's blocking it isn't Earth curve, is it?
the problem is we don't know where the boat is, right? Like,
Well, you do, because you can
Well,
measure it
forget
with the
whether
mass.
it doesn't matter. The distance is irrelevant. What he's demonstrating is obstruction, as we keep having Dawn point out. Yeah, we are. That's what's being demonstrated. But are you going to tell me that below where his mouse is now, that's Earth curve blocking the boat? Is that what you guys are going to tell me?
no, I don't think so. I mean, it looks like there's an inversion layer which is blocking the bottom of the boat.
Correct, which is what we describe when we talk about refraction. You guys talk about things going behind Earth
No,
curve,
of course.
right?
No.
So let me just finish on this point. Let me just point something out here. If there was a mountain in the background, or a piece of land, or a beach, right, that was 20 miles away, so 10 miles further away than this boat, right, I would not be able to see the sandy parts or the rocks or the people sunbathing on it, precisely because of this dirty air that's in the way.
I agree.
It would be blocking my line of sight to them.
In fact, actually, the reason why I wanted to talk to you guys about this is because I was able to actually model this using my refraction program.
Okay.
Cool.
So I do agree. That in this, you can get this sort of miraging, which would actually hide stuff in this manner. So the question is, though, what other things can we use to distinguish between the flat Earth and the round Earth, right? Because clearly both models will have this sort of refraction, right? And we don't know where the actual horizon is because of this refraction. So just because the boat appears to be on the horizon doesn't necessarily mean that it's actually at the globe horizon, right?
Well, this is assuming that we have a horizon that is closer to us, right?
No, I'm just saying because we don't know where the actual horizon is because of the refraction. So we don't know if the boat is actually on the hypothetical sphere horizon or if it's on some point which is actually closer. Because whenever I model this sort of refraction on a sphere, what happens is the horizon, the hard horizon, actually is closer to you than the actual horizon, like the theoretical bulge.
Yeah, that's what I was talking about. Exactly. So the actual horizon, as you describe it in your model, is something that is nowhere near the item that you're targeting, in this case, the boat.
Nathan, real quick,
Well, that's we don't know where the
I'm getting
boat
on
is.
Event Skeptic sock on my computer, so
Say that again.
Wait, what?
That's me. Don't kick me.
Oh, all right. Okay.
So
thanks.
I guess what I think would be more fruitful in this conversation between everybody would be to move away from the actual horizon and try and look at observations which are above the horizon, because the horizon is very misleading in both models. I mean, there's some actual quantitative predictions that I've been able to actually figure out. So, for example, if you actually do the Theodolite experiment, the Theodolite seems like it should actually level to somewhere near the center of this inversion zone on a flat Earth, because that's where stuff is being hidden. And like if you think about it, the Theodolite's parallel to the Earth on a flat Earth, and that parallel line kind of gets extended out, and it kind of, well, actually, let me just show you a picture. It'll be easier. So, okay. see. Okay, let me rerun this again. Right, so give me a second to actually explain what I'm actually showing here. Oh, come on. Don't do this to me. Show the darn graph. There we go. Can you guys see the graph?
Mm-hmm.
Yep.
Okay, great. So what I'm doing here is I have, these are kind of rays, and what I'm doing is I'm modeling an inversion layer, kind of like what you'd see in reality. So basically I have a very long, this is distance in meters, and then this is height above the water. And this is clearly not to scale, right? Because this is 600 meters, this is 50,000 meters. But basically, you see this white space here? This is basically this vanishing zone that Arwen talks about, right? So these are light rays which are going to my observing point, which is right here, and no ray is ever actually coming from this region, which means that anything in here would actually be invisible. And what I show here is I color the rays based on, well, okay, let me just, sorry, I didn't really prepare for this, but basically I'm simulating land here as being green, and then sky as being blue rays. And so if light rays hit above, or below 100 meters above the surface of the Earth, then I'm going to color them green. And if they're above that, I get something which is like the sky, right? So this is kind of simulating two different parts. And so you see how these rays kind of show the inversion that's happening, right? I've got rays which are hitting the top of the land, which if I follow them, they're actually going to go below and then come back up. Right? You can kind of see these lines are converging, and then they're going to start to go underneath.
Are you saying the light's bouncing?
No.
It's basically bouncing, yeah.
Okay.
And then these light rays are going to come and hit the observer, right? Sorry, I'm doing this by hand, but you see exactly what I mean. And then you see how I get like this floaty land effect, right? Because basically the light rays from the sky are actually coming below the light rays in the land. And then all these rays are actually a reflection of the things above this red line. And then you see these blue lines here are light rays which actually hit the water. So this would be kind of the hard horizon, right?
Yeah, that's what Arwen calls the first slant zone, I think.
Right. So basically, you see this red line. This red line is where the theodolite would level. So
Gotcha.
this is the ray that I would see. And you see that it actually goes right to, if I zoom out, it starts to basically follow the bottom of this vanishing zone. So basically, if you took a theodolite and you went out, you centered it on, you leveled it at your height, and you looked at the obstruction, you should see basically the crosshair being right in the middle, or like right in the midst of this miraging effect. But on a globe Earth, because the curvature is happening, there's no correlation between where the theodolite levels and where this mirage actually happens. So that's like one quantitative difference between the flat Earth and the globe Earth, which you can actually go out and measure.
Excellent.
And another thing that I'd like to point out basically is going to be relevant to our discussion of the peaks. And if you see these lines up here going to really high altitudes, they're not affected by the refraction whatsoever.
Indeed.
Yes. And this is the same as the sphere Earth. So again, I can kind of model the same sort of deal in the sphere. Right, I get the same, similar kind of vanishing zone happening down here. This is an observer very low to the ground. But you see the rays up here are actually like perfect. So if we want to avoid any fuss with like dealing with, you know, the refraction and all this nonsense. It's useless to try and talk about this the actual like near the horizon, because it's just too messy, too complicated. With the exception of this theodolite thing, right? This theodolite measurements, I think that's going to be the clear difference between the two. Because let's just rerun this for a higher height so it doesn't look so weird.
When you get to the end, I've just got a couple of questions, if you don't mind.
Sure thing. Yeah. I understand. I did not prepare for this in any way, shape, or form, but I just wanted to show you guys kind of some stuff that I find very interesting. Okay. Oh, I went too high. Or no, I didn't go to long enough distances. Let's do 50 kilometers. Okay. So here I'm just plotting like the temperature gradients and the index of refraction, just for information. And yeah, okay, so here's the floaty land. These are distances that are comparable to the Isle of Man observation. So you can actually see, if you put a tiny inversion layer, you can kind of get and like what Riley saw on a globe Earth as well as a flat Earth. That's just something to point out. That's nice. Right, but here you see straight lines going up to 600, 500 meters, right? There's no effects of refraction. Okay. Great. That's basically all I have to say.
Okay, first question.
Oh, wait, no, sorry. One more thing. Here's the theodolite ray, right? So like the vanishing zone is down here, and the theodolite is like pointing way up above where the actual like refraction zone is, precisely because of the curvature of the Earth, right? Curvature of the Earth means that the level is slightly above, and the land kind of drops below. And so the theodolite will actually be nowhere near the inversion layer.
How far of a distance were you using are you proposing to use a theodolite though?
You're roboting, Tim Osman. Is that you talking?
It's kind of hard to say, but I mean, if you look, like this is 50 kilometers. That's pretty far for like a theodolite, but I think maybe 10 kilometers might be, I have to do some more tests and modeling to see side-by-side comparisons. But I think even here you can kind of see that like the deviation is pretty far away. But yeah, I think you have to go, I think you have to go pretty far out, right? Because you basically want to be in this area where this ray is basically following the vanishing zone.
Okay.
But you just have to look at the beach, and you just have to find a target in the distance, like these windmills, right? Like these windmills are perfect because they're right near the vanishing zone, and you can actually get them pretty easily. They're like right in this inversion layer.
Exactly. The bottom of them is, and sometimes the top of them isn't, depending on the distance. But,
right, exactly.
So my couple of questions are, so first question, in terms of the lines that you're drawing to the top of stuff, when we were on Steve's show, there was a lot of kerfuffle because they couldn't draw a straight line to this stuff. Because in essence, if you do draw a straight line to anything, you're proving the Earth is flat, because obviously it's going away from you on a curve. So they had to apply an arc calculation to stuff that was, when measuring on the y-axis up and down vertically, they're having to apply an arc calculation to it. So in your model, is it literally going to be straight lines?
Well, no, I just mean in terms of what you can see. So the light rays are not being bent significantly by refraction. So like in terms of if you wanted to measure angles, then yeah, I mean, you can't really measure the absolute height of things because you don't know where like the bottom, you can't find the bottom of the object, right? Because it's being hidden by the horizon. In both models, actually, right? In both models, the bottom is being hidden by the horizon. So I find it very odd that you should be able to measure the height of something very far away, because you need to be able to establish the angle to the bottom of the object as well as the angle between the bottom and the top. Do you understand what I'm saying?
I mean, I still haven't asked. I know I've got that on my to-do list in terms of things to ask Chris, but I haven't asked him yet because I haven't spoken to him.
Okay.
But I do, since racking my brains, remember a vague idea of why he could get the bottom of things. And that's because he was using the same datum in both instances. So this was tied together after the fact, but I realised during the debate process the significance of using the same datum. So if you're going to use Google Earth on one side, you use Google Earth on the other. If you're going to use Ordnance Survey on one side, you use it on the other, because they're all tied to the same datum.
Yeah, that makes sense.
So that's, I don't know how Chris has done it, but I do remember him explaining that to me and saying, I've used the same datum on both sides. I can use a different datum if
they
you
have
want me
really
to.
accurate data. The UK government has like that entire region mapped out with very high precision. It's just a bit, it's a bit involved to try and decode all of that stuff. So
Sure, but the point that Chris was trying to get over on that particular debate on Steve's channel was that if you do take a straight line measurement to the top of Snaefell, by doing so you're in essence proving that it's flat. And the way they got around that was by going away, putting their heads together and working out how to do it with an arc calculation. But as you rightly say, as soon as you do that, you can't take an angle. You can't take an angle from an arc.
Well, I guess I'm confused as to what you mean by measure the angle of the object, because you have to measure an angle relative to something else.
Correct.
And like,
well,
I don't know. You can measure the angle with respect to the horizontal, like or the level, right? That's one option. But that's just setting your zero mark. And then to gain any other information, you need to know kind of the angle to the bottom of the object as well.
Right, that's what I'm saying. So you use the datum to get your 0 point on the same plane. That's what you're doing when you're using a datum in that regard. It's all tied to a flat plane. This has also been debated. So when measuring to the top of stuff, you're proving it's flat if you don't factor in, back to the beginning of this debate, the cumulative drop. So you take a straight line to Snaefell, and then you take a straight line to, I've forgotten the name of the other mountain, but the mountain that's closer than Snaefell. And what you're doing if you take a straight line to both is measuring it on a flat plane, because you're not factoring in the cumulative.
Not necessarily, right? Like I can find the angle between my horizontal and those objects on the sphere, right? Like it's just whether or not they are, let's say, if there is a drop, right? Then depending on your distance, Snaefell might be lower or higher than North Barul.
Well, correct.
Relative to that horizontal, right?
To extrapolate the data, I see what you're saying. So you do draw a straight line, you're measuring it on a sphere, you measure your straight line, and then the outcome shows you whether or not you have any accumulative drop.
Right. You measure the angle from, well, you don't even need to know the absolute angle, right? I'm pretty sure you should be able to make a conclusion based on the difference in angle, like the apparent positions, like whether or not one is above the other.
Sure. I mean,
given the distance you are away from them.
I'm extremely confident, having seen it modelled on a flat plane and had Chris drawn straight lines to all of these different mountains at all the different distances three-dimensionally. And as I say, it works out beautifully on a flat plane.
At a certain elevation only.
So again, Tim, you're roboting a bit if you speak slowly.
At a certain elevation only.
I think your connection's poor or something. What happened? I don't know why people robot like this, but yeah, no, I understand.
There was one other question I wanted to ask you. Sorry, just before I forget it.
Oh, sure. Yeah, so go ahead. Yeah, let's
from your first, you said, "Oh, I'll go up higher to show how this is negated," and you did, which is great because that's now dedicated to air. But in the first example that you had, and you were saying that Theodolite gives you a spurious outcome, shall we say? If you were to do it with, for the sake of argument, something that was if you used a laser and literally just pointed it, rather than measuring what you see optically in a lens, if you were literally to fire a laser across to the other side, would that not be more useful?
The path?
Say again?
And then follow the path of the laser?
Yeah, precisely. So see, if for the sake of argument, you were to say that based on being at, say, 100 feet at some Bs and looking out at the lighthouse, let's just for easy numbers say that the lighthouse, the base sits at 100 feet also. If you fired your laser across that body of water and it hit the bottom of the lighthouse, that would be far... I'm asking more than saying, asserting it. Would that be more useful than a theodolite reading.
Well, I think the problem is if you did, I mean, I would be very surprised if the laser would actually hit the bottom, because that would mean that the atmosphere would have to be incredibly uniform over such a large distance. Like, my expectation is that the laser on any model, doesn't matter, the laser is never going to be perfectly straight, just because there's so much changes in the atmosphere over that long of a distance. Like, so that's why pointing things at the horizon and trying to deduce stuff from there is incredibly messy. And you actually need to take observations over long periods of time with many different weather conditions in order to actually come to any conclusion, because of the atmospheric effects. Because you basically need to just average over all of the different kinds of atmospheres, atmospheric conditions that can happen.
So what about if it was repeated then? So I'm just trying to think of ways of being able to measure the bit that you're saying is the difficult bit. So the bit that's got plenty of refraction, invisibility zones, all that kind of stuff. If you're saying, well, no, a laser just simply wouldn't cut through all that, then yeah, fair enough, it might be a redundant test. However, it might not be. I don't know without doing it, and I don't own a laser. Right. I think well, basically, if you can get a theodolite which has a decent enough zoom, which I think these things have telescopes on them, if I'm not mistaken. Yeah, you can get high zoom theodolites.
You need to look through them, and then you need to see, do my crosshairs line up with this inversion layer? And that's, if you look at something far enough in the distance and you see it partially obscured, kind of like what Ranty has with this boat, and it has to be far enough away. I mean, that's another issue, right? If you're too close, then both models basically look the same, because the Earth is, if you're over a certain, let's just say if you're, if the bulge is very, very small, right, then, it's basically flat anyways, and it will look flat. So you need to look at objects which are sufficient, like, above
30 miles. Do you not think that
20 miles
Lighthouse
away
is right in that sweet spot? That's about perfect. 30 miles, you've got a significant amount of drop and bulge to be factoring in. So I think, I just think that is a really good distance.
Did a laser test, didn't they, recently?
Say again, Don?
Yes.
Flat Earth Core just did a laser test recently.
Right, yeah, and I think the atmospheric conditions there are actually a little bit different, and that's one thing that I actually wanted to test.
24 kilometers over ice, and no results as yet.
Not yet, no. They will release them though.
Well, so I talked to a guy on the Discord, and it was interesting.
I think if they really got the laser on the other side, they would have released it already, wouldn't you?
Not necessarily.
Well, no, it was interesting.
Well, yes, necessarily. It's important evidence, isn't it?
Before we drift off topic, could I just present Nathan?
You are.
I'm just going to ask Philip, if I had a theodolite now, where would I place the crosshairs? Where would you tell me to place the crosshairs?
So it would be. So it should be at least. Okay, I'm just going to make a guess, because I would actually like to try and render an image to see what it would look like kind of using my program to actually render this. But I would say, you see where that kind of line of mirroring is? It would be somewhere like either, I think it's slightly above that, but it would be definitely in the miraging zone. It would be very close and be in the middle of all that.
Yeah, I'd place a bet as right in the middle.
Okay.
I don't think it's right in the middle, but I think it's going to be
close enough.
Definitely within.
So basically, nobody has any idea where the horizon is.
No.
Essentially.
But that's the problem. That's what we're trying to get to.
This isn't flat Earth evidence.
Well, just because the difference
none of us are trying to present it as
putting the crosshairs there, and the difference between putting the crosshairs there is going to make a difference of living on a ball that's, if we did live on a ball, living on a ball that's 1,000 miles in diameter, or a ball that's 5,000 miles in diameter.
No, Ranty, the point is that if you were to do this on a ball, for any given height, there would be little to no correlation between where the miraging zone happens and where the crosshairs would sit. Actually, the crosshairs should sit above the miraging zone, if anything. But
so
if you lived on a
leveled, then where would you say it was leveled?
It would definitely be above. It would be above. I don't know exactly how far, but it would be well above the. It depends on how far this boat is, but it would be above whatever the miraging zone would be.
How far's
And
the
on
boat,
a
Ranty?
globe, it would eventually just point out into
Well, that's
space.
just a
It wouldn't really
presupposition, isn't it?
hit land hardly at all.
No,
It would
no,
just
it's
go
not
up.
a pre. I mean, well, okay, yeah, you're asking me what it would be like if the Earth was a globe, and that's what
Yeah,
it would.
that's correct.
Yeah.
So if we were level here, then you know, and I'm looking through this telescope at this time, and I'm seeing all this crazy stuff going on with this boat, and I can see these waves here, right? Are you trying to tell me that these waves are not the hard horizon? That this is the horizon?
No, no. What I'm saying is that there's a difference between in the flat Earth model, the horizon is where your eye level is, and your hard horizon is going to not be the same as your eye level on a flat Earth model because of the distortion. Because there's just no way those light rays from the actual ground should be able to get to your eye precisely because of the vanishing zone.
There's distortion on both models. This doesn't show anything either way.
Yeah, that's exactly
But
what
on
I'm
a
saying.
round model, those rays would eventually go out into space, and you'd have different zones depending on your height. You'd see a different set of light rays at one height, see a different set of light rays
No,
at
you
another
do.
height.
You do in
and
both
stuff would
models.
vanish and come in.
You do in both models, right? Because what happens is as you go up on the flat Earth model is that vanishing zone gets pushed back farther, so you can see things at lower heights.
Exactly.
But
Right.
on the globe model, you'd basically have stuff disappearing and reappearing depending on which zone you're in. When miraging
No, it's
affects
the same.
stuff in
It's
your
the
height.
same sort of thing. It's just in one model you have an actual obstruction, a physical bulge, and then in one model the obstruction is caused only by miraging. It's just there's in both models as you go up you can see farther because the mirage and the bulge gets pushed farther back. But
Hey, Peanuts, can you hear us?
Hey, wait, what's going on?
Good to have you.
So, could I ask where you would say the horizon is on this image? This is the video.
Why do you want to ask that? It's the same answer.
Well, we've got 3 different layers here that you could say
Yeah.
are the horizon.
All you're
Yeah,
showing
exactly.
is that there's some discrepancy around the horizon at some times. That's normal
Correct.
on the
All
global.
times.
No, not at all
But you're
times.
saying on both
all
models
times.
we have this problem, which is why
Yeah,
for weeks
I don't
we've
know.
been
I mean,
saying you need to get higher up.
I don't know what happens when you have multiple inversion layers like this. I haven't actually modeled that, so I can't really say either way.
But what Ranty's showing is this is the reason not to do stuff at the beach, because you get these inversion
Yeah,
layers.
exactly. Yeah,
You know, and
but I mean that's
completely agree.
everyone's agrees on that.
Well,
Actually,
no,
that's really
no,
cool.
No, not at
That's
all.
like-
We've got someone called Slice Barkane who doesn't understand A, that everything in the Isle of Man is looming, and B, he wants to tie everyone's feet to the water and get all of these effects so he can call them curvature. It's basically disingenuous, but we do have people that absolutely want to get us tied to the beach.
Well, Sly doesn't think this can happen on a flat Earth. Would completely disagree with him as well. Just nothing against him, but like, yeah, it's a lot more complicated than just.
I'm in the middle. I don't care. Like, you have to prove that it's possible on flat Earth and how if you want us to believe that.
Well, my modeling shows that this sort of effect can happen on a flat Earth if you have the right conditions. So that's another issue, is that it's really hard. Like, it's really hard to know what the conditions are. But the problem is on a flat Earth, these inversion layers have to be very large in order to get the large amount of hidden. Basically, like the thickness of the warm air layer has to be much larger on a flat Earth than it would be on a globe Earth to get this miraging effect. In order to actually get stuff hidden in the first place. But that doesn't mean that it's impossible. It just means that, like, if you have a very nice day where there's lots of where there's very little miraging, and it seems like you should be able to see much farther, you know.
This miraging doesn't prove
Philip.
flat Earth. I'm sorry.
Go on, Peanuts. Hey, go ahead.
Hey, Philip. I was just saying, man, I've been listening to you, and I can really agree with you when you say, basically there is no pot of gold at the end of a laser test. There is too much divergence. You don't know what the beam how it's refracting. You don't know what it's doing. So it seems like a test that's not confirmable. Now, could you tell me what's the possibilities of versus we're seeing something being distorted versus what we're seeing is being lifted up behind obstruction?
So I think one misconception is actually how much things need to be lifted up. It's actually not a lot. So it's a very, very tiny amount of lifting. Versus when you get this miraging effect to like hide stuff, you need a significantly large inversion layer to get the amount of hidden amount of obstruction that you actually see in these images. Now, that's not to say that that's not what's happening, but no one's ever really measured the atmosphere on a particular day and then done an observation and confirmed that that large inversion layer is there. So,
well, let me ask you this. So on the refraction formula, we're assuming the radius is there, right? Because you have to have radius for that formula to work, right?
Sure. Yeah.
So one other question, and I'll leave. Light bends up, but does it also, can it bend down?
Yes. In both models, it will bend up and down. It depends on the atmospheric conditions.
So we can all agree that in that formula, you have to base assumptions, correct?
In that
it's just like a laser test. It's just like a laser test. You can't measure the divergence, so the beam changes. So it seems like it's self and self.
So the formula is assuming that the atmosphere is generally getting cooler as you go up, and as you go up, this is what you generally experience, right? Like if you're on an airplane, you know that the atmosphere outside's a lot colder. And so because you know that things are getting cooler as you go up, the atmosphere is actually getting, let's say, less dense. Wait, that doesn't make sense. Wait, hold on. Oh, the pressure is also decreasing. But basically, as you go up, the atmosphere, generally speaking, gets less dense, right? And because of that, the index of refraction of the air generally gets lower. And so under those conditions, if the index of refraction decreases with height, generally speaking, light rays will kind of arc down, will kind of bend downward because they're trying to take advantage of the fact that the index of refraction is lower. So if you think about a light ray, it wants to get between two places in the fastest amount of time. And the higher the index of refraction, the slower the light moves. So if you're looking at trajectories of light, they basically want to stay in the low index of refraction for as long as possible to get from point A to point B as quickly as possible. So when you have a decreasing index of refraction, you get arcing downward because it wants to spend more time higher up. And then when you get an inversion layer where the index of refraction is actually lower near the surface of the Earth, the light rays will actually go down and bend up towards the observer because it wants to spend time down below near the low index of refraction to go reach the observer fastest. So, I mean, it all depends on the atmospheric conditions, but generally speaking, if the atmosphere is getting less dense as you go up, light rays will arc down. And I think that's kind of the origin behind that formula.
This is
fundamental to a sunset.
This is Fermat's principle on the trajectory of light, in essence.
Yeah, exactly. Yes. Mm-hmm.
And when you say that it arcs, do you mean arc like a hula hoop in a curve, or do you mean bend at a V? Because I thought that light propagated in straight lines, not in arced.
No, it depends. So yeah, it's Fermat's principle, which says that if light is moving through an inhomogeneous index of refraction, it's not going to travel in a straight line.
So there are things like curved lasers and stuff like that?
Yeah. I think I presented one the other day where there's actually they made the laser actually bend in kind of like a parabola, kind of like a ball shape, like the trajectory of a projectile.
But
that's because the index
I just want to get this tied down though, Phil, just for this part, because I know you're honest in this regard. Right, light travels in straight lines, and though it may appear to curve, it is going through multiple layers, and that is what is happening in terms of you have Snell's law bending, not bending, changing the angle of light, and you have Fermat's principle on the trajectory of light, making light take the, let's call it this, easiest path. So when you look at it, it appears to curve, but it isn't. It can't. Light doesn't curve. But it can change direction and appear to the observer as though it is curving.
Wait, I'm confused. What do you mean appears to be curving?
Well, if you were to look at it and you had smoke, so let's say use the laser light example. If you literally fired a laser across and you had smoke across the whole of the bay, you could look at it side on and see it appearing to look like it was curving. The same principle is really easy to demonstrate if you show the sugar tank experiment, where you have a density gradient in the sugar tank that has settled over a time, and you're left with many different layers of density in the sugar solution, and you can fire a laser through it, and side on it looks like the laser's bending. Obviously it's not.
I see what you're saying. Yes. So that's because right, the laser light that's actually hitting your eye is probably moving in a straight line, but that doesn't mean that the laser moving through it is still bending, right? It's still. That's why in the miraging effect, things don't appear where they actually are, right? If I have this inversion layer, like it's not like the runner literally is being reflected down below above this, like, and floating above this layer of air. No, it's because the light is being bent to your eye in a weird way to make it appear that way.
That's to your eye is the same way as me saying it appears to.
But I mean, light. Well, to be perfectly clear, light actually isn't a ray, right? Light is actually a wave. So all of this bending stuff, light bending and all this nonsense is kind of an approximation of what light is actually doing. But in reality, like the light is the light is not actually traveling in a straight line. It's kind of curving through the atmosphere in this weird way to make things appear as if they're not where they're supposed to be.
Is the light curving, or is it just reflecting a bunch of times in like a laminar stream of atmosphere? Because couldn't it be ping-ponging inside of a curved stream of atmosphere, but still be propagating in a straight line within the curved way?
Yeah. These are all. I mean, like. It depends on how far down you want to go, how closely do you want to follow the light? Like, do you want to follow like it on like a very small scale? Then yes, on a small scale, it's like traveling in a straight line, and then it gets bent a little bit, traveling in a straight line, gets bent a little bit, and that kind of adds up into a cumulative curve.
Because it kind of begs the question, if light's bending, then wouldn't there be prisming if the light is actually physically bending itself? Wouldn't there be a rainbow effect on the outside of the light curve, and on the inner side of the light curve, wouldn't it, I don't know, laser and concentrate or something?
That does happen.
I think there is a prism. I think there is a very slight prisming effect, correct. Because the different wavelengths get bent more or less.
And then that kind of begs another question, like once light is bent and broken up, how does it come back together? I've never heard of light bending up into prisming effects and rainbows or whatever and coming back together again.
Well, it's very slight. I think when it comes to the atmosphere, like if you're shining a laser through a prism or shining light through a prism, that's like a really high index of refraction. But if I'm talking about the atmosphere, the changes is like in the third decimal place of the index of refraction. So like the amount of change is probably very, very small between the different light rays. You'd have to go to, let's say, like radio frequencies or microwaves to see a significant difference in the amount of bending.
But do you not see why Anthony gets so frustrated, and I get so frustrated, and many others get so frustrated with the automatic insertion of 7.6R?
No, I completely understand. Yes.
Fair enough.
Because it's complicated. It's very, very complicated.
Well, it's spurious. That's what I would say, not complicated. Yeah, maybe, but
well, yeah. I mean, you have to prove the curvature in different ways. Let's just say, like, I mean, yeah.
Hey, so say Philip, you said the higher you go, the less dense the air is, and it's cooler, and obviously less molecules.
Yeah, so less refraction.
Okay, so I don't know how you would do it, but is there any test that could be done that's up? Like,
well, that's why. So I was talking about this the other day. So looking at the peaks of mountains, you should be able to see the drop a little more obviously, because there you actually avoid the effects of refraction, and you can actually you should be able to tell, at least whether or not there's some sort of curvature happening. You have to worry about perspective, obviously, and all that stuff. But at least it gives you a place where you don't have to worry about bending light and all that nonsense. You can just say, look, there's the mountain. This is where it appears to be. That's where it actually is. And so let's draw some conclusions from that.
I totally agree, and it's basically all of the explanations we're talking about in this regard in terms of refraction and obstruction. If you're looking out along your theodolite, we're talking about anything below that line. Simple as that. And everything above it, therefore, should be free from those effects. In other words, you can see infinite distances when you're looking up, when you're above that horizontal line. Therefore, the mountains definitely fall into that category.
You still run into issues of like light attenuation, so the atmosphere absorbs light at long distances. But yeah, I agree. You can see farther.
And same applies to angular resolution. If you go too far, suddenly you've brought the thing that's considerably far in the distance to the horizon anyway, by virtue of its size decreasing at distance. So you can force things into this zone if you go too far.
Yeah,
that's
exactly.
why I think the Isle of Man is absolutely ideal in that regard. About 30 to 40, maybe 50 miles is perfect for this sort of observation.
And it's like 600 meters above the surface of the Earth. So
Philip, just kind of off the side, when I grew up in the 80s, and I rarely remember watching Bill Nye teaching about boats going over the curvature. So I mean,
I've seen that clip.
But do you honestly think that is using the scientific method when we were taught that?
So that particular demonstration, or
basically, I'm telling you that I was taught as that it's a fact that boats disappear bottom up because of obstruction of the Earth. And so what I'm asking is, do you think that the scientific method was used, or do you think that we were just told that?
I don't know if there is a lot of scientific literature actually even looking at this sort of thing, because I think the scientific community is pretty confident that the Earth is a globe. So that sort of applying this scientific method, there's not going to be any scientist who's going to want to spend time looking at a ship going over the horizon.
So you would agree that stuff like boats over the curve, that's all taken in an assumption that somebody has went out there and used the scientific method to find this out. So they're taking it as a fact, right?
So I think a better way of saying it is when you're doing observations in the real world where there's a lack of control, you have to be very careful about if you want to be scientific, you need to be able to make the observation many different times. You need to be able to understand what's happening with the atmosphere. You need to be able to take into account all the different variables that might actually be there in order to be scientific.
Okay, so
if someone says
just give me.
If someone says I saw a boat go over the horizon once in my life, that's not the scientific method. It's
Okay,
it's just one observation.
Just give me, I understand. Just give me a yes or a no. Do mainstream scientists take the assertion that boats disappear over the horizon because of obstruction of the Earth? Yes or no? Do they take that assumption?
If I asked a generic scientist, they would probably say yes. That is evidence that the Earth is curved.
Okay.
Yes.
And so basically, as of today, there is no experiment that we can observe that 100% use the scientific method to show that this is a fact, right?
I don't know if there has or hasn't been an experiment that has tried to do this.
Well,
I haven't.
Okay,
to be honest, I haven't
so
looked.
at least one that we're not aware of.
Like, I've seen videos of ships going over the horizon, and they seem, at least in my conceptualization and how I understand the atmospheric refraction, it seems to match pretty well with my modeling. But you know, I have to. If I were to try and say that that is the scientific method, I would need to put in a lot more effort into trying to make it work.
So Randy's got up an example right now, and what we have is wind turbines going into the distance, and obviously they're further and further into the distance. As they go further into the distance, you can see it's visually obvious. But they're technically...
Yeah, I see that. That's very interesting. So why are they kind of tilting like that?
Well, here's what I'm doing now. I'm looking down this row of wind turbines here, from this location down here, and I pan across and I look at all these, all in straight lines. I'll show you the video, just a few seconds of it.
Yeah.
So there's the ones on the right. There's the next ones we just skimmed by them, and there's the
So we're looking at them more and more from a different angles, but I like those ones which are kind of like directly on with you.
Yeah.
No, not these. The first ones
I've got an example for these though. I've got two examples actually. One for these. I just want to show you for an angular size. What I've done is I've put the hard horizon in here. You can see how this one is nearer, obviously the nearer turbine, and this is the one that's further away, but it looks smaller. Now I've put a line, thick red line through the middle of the hubs, and what you'll see is that as we go to 11 miles, basically past the very first turbine, the angular size has decreased so much that we no longer see it due to angular size and perspective, as opposed to it going over the curve of the Earth. Now, the curvature calcs on this say that at 10.3 miles, so at this point here, this is where the turbines will disappear and go beyond the curvature of the Earth. However, when I've worked it out, literally 1 mile further down the line, hardly any distance further, is where the angular size difference will also give that same perspective of it getting smaller and smaller and smaller.
So my question is, how do you know it's actually perspective which is causing these things to sink like that?
Well, if you go back to the first, Randy, you can go back to
these turbines here, right? So these are the ones that you were talking about. I'm assuming these are the ones that you're talking about, right? So, in your opinion, these are actually going over the curve, and because I also took another observation from this location here, and I looked at them side on.
Yeah.
And I looked at the same wind turbines, and I looked across here, and I've actually got the image up for them, which is this one here. Oh no, it's not. Where has it gone? This one here. So this is the one from the side. Now the red line is the one that's the nearest to us, obviously because it's the higher one, and each individual turbine backed out. I think it was like 3 hang on, I might have them written down somewhere. Which turbine? Sorry, 2, 6, 9, 13, 16, 20, 24, and 20. So in that particular order, those turbines that were nearest to us. And so what I did is I placed a red line through the center of the hubs on the ones that were exactly on that line, and this red line goes through the hub of every single turbine in a very straight line, and it also does it on the other 4 sets of wind farms. So when I viewed it from this location, looking at it from here, all these turbines were in a perfectly straight line, row 1, 2, 3, and 4. And also when I looked at them from this location, which was further away, again, they were all perfectly straight to the hub. Now, I've got an example of that ready to go with the one on the left, which also has the line going through the center of the hub. This is the left turbines.
Do you actually know how far away those things are? Because you could use
11.5
perspective to predict what that line should actually be.
Okay,
given
so
the heights of the windmills, like you should be able to compare this exactly to what you should expect for perspective.
It's all on here. The distance in miles to each turbine. So to this one here, it's 11.55. This one's 11.85. To the furthest one, 13.7. This is the curvature calcs that says how much the turbine should have dropped behind the curve of the Earth, right? 64.28, 68.27, right down to the furthest one that would have done at 95.52, right? However, and you can also see these are in a perfectly straight line through the hub. So not only did I get them looking straight down them from 11 miles and 13 miles away, I also looked at them from the side and saw there was no curvature. And lastly, I want to go back to this same image, which proves that the angular size would have given pretty much the same curvature calcs in comparison. There's the angular size change, and there's the curvature calcs here. Almost indistinguishable. So what I'm saying is that they've co-opted angular size for curvature of the Earth.
Oh, so you're saying the curvature matches the curvature matches this red line?
Yes, it matches the angular size change to within a few degrees.
Oh,
you know what I mean, literally, this point here is where the curvature calcs say we should lose contact with the turbines. However, this point here is where the angular size will have also made them disappear from view.
No, I mean,
so small.
How do you know that red line is supposed to be the angular size, though? I mean, you're basically assuming that that's what's happening, but you have to show what the prediction would be for perspective as well on a flat Earth.
Well, this image here, it's the same image that I was using. The horizon, obviously, I adjusted the contrast to get the horizon. And what you can see immediately, especially on this one, this is quite clear actually, you can see that the pointing downwards.
I mean, this is unequivocally a demonstration of perspective, because you cannot tell me that it's anything other than perspective when you go to the side elevation. So if Ranty now goes to the side elevation, these things aren't on a curve, are they?
Yeah, I mean, that is very interesting. Like, it looks
flat. Yes,
it's like it's
as a pancake. I'd agree.
It's not just curve. It's not just curve. It's also perspective, right? Because they're going to be mixing the two.
No, I'd just say it's just perspective. Because this is, you can't have that argument unless you see a curve when you look at them side on. So these would need to be adhering to that curve that you.
So is this one image
from the other angle?
Is this one continuous image?
This is from a video. This is from a video. I've got the actual video. I can show you if you're interested, or you just take for it.
Okay.
I'll put the video.
That's really interesting, guys.
That's amazing. That's amazing right there, man.
Yeah, well
I
done,
actually
Ranty.
have to go, but I definitely will be back to talk more about this because that's a interesting observation. All right.
Okay. So this is me basically on the beach at.
Okay, I'll talk to you guys later.
Okay.
Thank you,
Philip.
Yeah, no problem.
Star as ever.
Bye.
Brilliant information. Thank you for your studying and homework and all the rest of it.
Yeah. All right. Talk to you later. Bye.
But yeah, as Ranty plays this video out, feel free to let it play, Ranty, just so it's dedicated to air. If you can just let it play once through, that'd be brilliant. Just stick it on from the beginning. It's only 3.5 minutes long. You might as well watch the whole thing play through.
Yeah, we don't see that. It's Blackpool Tower we're looking at.
Oh, okay.
First half.
Fair enough. But yeah, if you just let this bit play out. But the bottom line is, if you want to say that these wind turbines are falling behind a curve, you need to explain why they're not built on a curve, because they're not. They're built completely level, completely flat. When you look side onto them, they're not curving. So if you want to in any way suggest that as you look front on, where we're all told we should be measuring the curvature, not curvature, obstruction, well, you need to explain why they dip away when you look front on, but they're absolutely perfectly level and flat when you look side on. Because they are flat. Simple. You're not seeing curvature.
Ranty, how many miles is that, Ranty?
To this
on
turbine
on that side shot, how many miles was that?
Can you bring the
this
photo with
side
all the
one.
measurements up, Ranty? You've got a photo with it all. You've got it all written down.
Yeah. To the side ones, we're looking at 4 miles 76 to the furthest ones that was 6 miles and a quarter, basically. Go in the other direction. If we go to the furthest one here, which is this turbine, and we pull it back, essentially that's what, 13.
Wow.
13.6. So I caught them from both this side and that side, and basically the images show that I can put a straight line through them whilst looking at 13 miles away. So 11.55 to 13.7. This white line goes right through the center of the hubs the entire distance. And the same on the side elevation. When I do it from the side elevation, they go right through the hubs.
Yeah, that one right there. Like when you look at the lines, I mean, that's a killer. I mean, especially when you show, because you showed Philip the facing it a different way, and it showed it where it looks like it's perspective, and then when you show a side shot, this right here is what Soundly will never do.
Right on. Yeah, the bridge that he says is curving.
He'll never take a side shot of it because it I mean, it kills it.
Yeah,
it's obvious why he only
curving,
shows
it's
the
curving.
way the
If it's
perspective
curving
looks.
away from you as you look down the line, so if you bring up them all in a row again, the far left image, Ranty, if this is them curving away from you, each one of these represents... Hi, Overthought, can you hear us?
Hey, what's up? Yep.
Oh, good to have you. I was just about to boot you.
Yep.
I saw you on Anthony's show earlier, but we'll just round out this point and then we'll do proper introduction. So yeah, if you're to believe, what is happening here is each of these sticks is shorter. This stick is shorter than this stick. So in other words, this has disappeared, if it was a boat, hull first, over the curve, apparently, because it's further away, right? Wrong. As soon as you go to the side elevation, you see the real picture. This stuff's not built on a curve. It's absolutely flat as a pancake. Sorry. There we go. That was the end of that point. Over. What was your screen name again? Sorry.
It's Overthought. My name's Tyler.
Good
Thanks
to
for
have you,
having
Tyler. What can we do you for?
I just wanted to hold on. I got to turn this down. Okay. I just wanted to reiterate something that I was saying on Anthony's channel. For people who think that you could see things on hypothetically on a flat plane, if you can see things infinitely, like if you could see France from the east coast of the United States, whatever. I just think that's ridiculous because our eyesight, obviously, and the atmosphere and stuff. But I just had a hypothetical question, a thought experiment. Say you have the same eyesight, 20/20 vision, like a normal person, and you go down. This is on a hypothetical infinite plane. You go down to a millimeter tall. Are you going to see the same horizon as if you're 6 foot tall? And I just want people to think about that when they hear Bill Nye saying, like, well, duh, you can't see France from New York or whatever. It's just ridiculous.
Good point. Fair enough. Well made.
Well, I mean, it's basically like you said, you'd have a vanishing point based off of your height. And basically, if an object is really, really large, it'll get slightly smaller in the distance. Like with the sun, it's large and it's high up. So it'll get slightly smaller, but eventually it will reach a setting point where, the low height of your vanishing point from your eyes down will make the ground compete for the lower half of the sun's vision, and it'll appear to set, like with any large object, like a building on the skyline in the distance, or any large object in the distance, like with the sun or anything. And so stuff will only vanish uniformly within your field of view if it is within your full vanishing point at eye level. Like a coin will disappear within your range of view, or something that's like from probably within 12 feet will disappear uniformly. But anything bigger than that in the distance will typically tend to set if it's evenly distributed between the top and bottom of your vanishing point of vision. But the sun is so large and so tall, so high up in the sky, it appears to set. That's all. It's not the curve of the Earth.
Well, I think the point I really wanted to make is people think like you really believe that if you were on a flat plane that you would not have a horizon, and your horizon would be based on the lens of your eye, the resolution that your eye can pick up. If hypothetically speaking, if we were in a vacuum and on a flat plane in a vacuum, no air, I would admit that I think that you could have, if you had a telescope good enough that could infinitely zoom, you'll keep zooming and zooming and zooming, and you could see infinitely. But that's not reality, and we can't do tests on that. But I don't think that's unreasonable to think that way.
And that's also a very, very strong reason why mainstream and people that you see on TV promoting science and all this, that's what they always go to. They always say, "Oh, why can't I see this?" Because they want you to think that in your mind. They want you to think, "Oh yeah, if it's flat, I should be able to see, as far as infinite." You can't see forever.
It's a crux. It's one of the cruxes of the whole quote flat Earth conversation.
Right.
And they can't admit that, and that's what we really need to drill into people. It's like, you really think that a 1 centimeter tall person with the same like the same 20/20 vision as a 6 foot tall person, you really think they would have the same exact horizon? That's ridiculous.
It's based off of your height, and so people need to realize.
Well, it's the angle. It opens up the angle to allow your optics to be able to view it. That's what you're doing when you're going higher.
No, it's based on the sharpness of your vision and your total resolution of sight.
Yeah, that's what I'm saying.
That's why increasingly better telescopes can see farther. It has nothing to do with your height. It has to do with your sharpness of vision, how well you can focus, and it also included the amount of obstruction in the distance. If there's just mist, cloud, if there's too much moist in the air, then you cannot see that far because eventually it will be blurred up.
That's why my thought experiment doesn't include air and no obstructions. I'm saying I do agree. I honestly think that if we were on a infinite flat plane and no air, and you had a good enough lens, you could just keep viewing and viewing and viewing. But that's not how it is.
Technically, yeah.
Yeah,
true.
what you're basically saying is what you need is a nice clear day.
Yeah, you can see further, but my whole argument is everyone's saying it's like geodesy. Geodesy says that they prove the sphericity from an angular drop of the horizon. That's not scientific evidence of anything, because then you're saying that everything you look at in the distance is 100% a straight line, and that's just not true. And people know that. I mean, that's known. Like, things get obscured from the atmosphere. So it's just like viewing things is not going to give you any sort of evidence or proof of anything.
No, that's not entirely true. The difference in what is viewed from different types of clarity and different types of observer will yield what can be seen and how the differences are. And then that combined observation can give you a much better clue as to what the shape is most likely to be.
Okay. I would say, I mean, I would agree if you could know every part about the atmosphere that you're looking through, but you can't. It's just too far. It's too much distance.
Too many variables.
Oh.
Don't you think it's a coincidence that the angular size difference somewhat matches up almost perfectly to the curvature calcs?
They've got to co-opt something, so we know what they've co-opted. They have co-opted perspective. They have co-opted atmospheric refraction. They have co-opted everything that actually works in terms of what your eyes do and what you can actually see. And they've done a good job of it. You know, you've got to tip your hat to how well they've covered this up.
Yeah, but they're still always dependent on the one part that actually does appear like it is the curved the most of whatever you're going to see out there. So that's what Soundly does, for example. He just zooms in on that one part that seems to be like it's curved, while basically excluding everything else surrounding that part of view that does not show curvature.
Yeah, and another thing I was I forgot who I was actually talking to that on Riley's channel. They were talking about things obscuring from the bottom up, and that's not possible on a flat plane and blah, blah, blah. It's like all you have to do to know that that is possible, take a magnifying glass, put it up against the side of a flat table, push something backwards, like this. Basically, I got this from Rob Skiba. Push something backwards, and it starts being obscured bottom up. What I mean, so that proves that it is possible.
I did this the other day. I did this to do you remember, Ranty, to model your mountains and your wind turbines?
Yeah.
So I just did it on my table. So to replicate because obviously you're talking negligible heights of stuff comparatively with the distance. So I was using the edges of CDs. So to make it 3 times the height, you've got 3 CDs versus the height of the wind turbines, about half the distance away on this flat table. And yeah, you can easily do it, you know, with the lens above the level of the table. The stuff in the distance gets obscured. And I even got miraging effects. This is in the really small scale. I'll have to dig out the picture and show what I got, actually. I might save that for when we actually go back to that observation. But Ranty's hoping, again, for a clearer day. So it might be the case that we don't use the ones that you got already. But in future, I'm sure I'll dig out that model. But you're absolutely right. You can easily get those effects on a flat table, let alone, you know, at distances with all sorts of other crazy effects going on.
Yeah. And no, it's just so ridiculous that like people assert and put themselves in horrible, terrible positions by asserting that like that's not possible on a flat Earth. And it's like, do you know what possible means? Like, you can't just assert something's not possible because you haven't tested every single possibility. I mean, you haven't tested every single scenario.
I think
miniaturizing
the
the
school
observation
systems
does kind of, yeah, that is the proving optics. So if you can miniaturize the apparent horizon effect, that it starts to become proof then, because you can emulate it in a smaller scale. That shows the exact same type of effects as that you see in the large scale. That's kind of validated scientific proof of optics, at least.
Yeah, I wouldn't go so far as to say proof or anything like that, because it's just not.
If you can replicate it, and it turns out to be the same thing, that is kind of that adheres to the scientific method, really.
I like this guy. I completely agree with you.
Well, I feel like we got to take off the first layer of everyone asserting that they know something or that they know something is not possible on a flat Earth. It's like, no, that just doesn't. That's just not true. It's like, because you don't know all the possibilities. It's a fallacy.
Well, what they do know is that they don't want to submit to, say, a model that, where flat Earth leads, like maybe that they were wrong, or, all the way to the spiritual component, at heart, kind of like maybe the religious component of flat Earth or whatever, but even all the way to a creator who set the world in motion in certain ways, who put the sun in the sky with a flat plane covered by a dome or whatever. That's what people know, that they don't want to submit to that sort of a system.
Well, I don't submit to any type of dome or anything like that.
Yeah, it's different for everybody, but yeah.
I just think that this should be just about facts only, and no religious aspect should be used to promote this. You know what I mean? I think the person should decide that avenue.
And that's good for a person who's driven by truth and reason. That's fine, but you also have to deal with the spirit behind people where they won't submit, where they just won't, listen. You got to deal with that too.
Are you presenting? Oh yeah, sure.
No, nobody's presenting anything at the moment. Did you want to?
You're not sharing?
No, nobody's sharing anything. Why'd you ask that?
Sorry?
Why'd you ask?
I just went to the toilet and just thought I heard someone say they were going to share.
No, but if I send you something, do you want to share it?
What is it?
Just a picture.
Yeah, sure.
Okay, I've sent it you on Skype. If you can bring it up, that'd be really handy. Can't seem to email it to myself for some reason. It just doesn't want to load my email page. Can't figure out why.
Man, I was hoping Tim would still be on here. I was gonna see what he thought about that little thought experiment.
There we go. Don't know if you can see that. So the only bit I'm really interested in showing here is on this line here. So the mirage effect blocking half.
Is this what he was just talking about?
This is just a small scale something I set up to get a comparison to what we've got on this image here. So you've got the wind turbine and it's being obscured. You're losing half the wind turbine, and you've got the mountains in the distance that are approximately 3 times the height. So you've got 3 CDs stacked up on top of each other, and then 1 CD about half the distance. So this represents the wind turbines, this represents the mountains. Well, this is probably a better view actually. So this is the height of the wind turbines, so you're only dealing with a tiny height, and then that's the height of the mountains in this picture. This is what we're trying to replicate over here. You can't see my mouse, I'm sorry. Bottom right is the actual picture we're trying to replicate, but that wasn't actually what I was bringing this up for. The bit I'm trying to show is on the horizon. So my camera's above the level of the table, obviously, to take this picture, but you've got an obstruction halfway up the near CD. Yeah, there you go. Ranty's highlighting. Hopefully you can see that in the Hangout. What looks like the top edge of the table, and if it was a clearer picture, you can see it in the background on the speaker and various other things. But you've got like this mirage line.
It's me.
Hello. How you doing? Looking nice there, Daylight, Ohio.
What's up, buddy?
Sky, sun, moon, stars, usual stuff.
Yeah. Tyler, are you still on here?
Yeah, how's it going?
Hey, what's up, man? I was the one you were talking to in the magnifying effect. How come it doesn't magnify boats and ships and stuff like that?
How do you know it doesn't?
It does. They don't get bigger like a magnifying glass would make them.
How do you know that?
I can see that. Correct?
Can I try and answer that one? As you're saying,
I mean,
you're asserting that you just can't tell.
I was just thinking, I was thinking after the Hangout too, if it was a magnifying effect, we would get magnified landscapes and magnified boats, magnified, towers, stuff like that. And
we do get that. Yeah. We do get the magnified towers, and I think it's an angular size problem. So with boats in the distance, they'd just be too physically small to have that effect happen and still have them visible at a great distance. Whereas you can have this effect with buildings. I'm sure Rob Skiba did a demonstration of this, where he had a building in the far distance that was massive by comparative terms, it should have been considerably smaller, and it was
See,
being lensed.
I would like to see scientists actually look into this and do math and just based on images and see if things actually. I mean, we do see things obscure, distorted, and in my opinion, bigger than what they should be compared to what actually would be with only perspective. If there was, like, hypothetically, if there was no air. So right. I think that things actually are magnified. Yeah.
Okay, and then in your the distance, like from New York City, let's say the east coast of the United States, seeing over to Europe.
Yeah.
Let's say the moon, Europe is 3,000, I think 3,400 miles from the States. So if you had something the size, like I said earlier, the size of the moon, something that large sitting in Europe, would we be able to see it on a flat plane from New York City?
With no atmosphere? Yeah.
With no atmosphere.
You'd have to be tall enough, too, to get a new vanishing point. Because if you're too low to the ground, you're going to vanish eventually from low height.
But we just said with no atmosphere.
But also you're low to the ground. So 6 feet down, a vanishing point from being off the ground only 6 feet means you're only going to see so far anyway. Well, you got to get high enough in the air.
Yeah, if it's big enough.
I don't think. Yeah. Why is it that if we go up higher, things get closer? I don't believe that.
No. Your vanishing point is distributed evenly from the top and bottom of your vision. Your top half usually has like limitless space because you're looking up into the sky and there's no ground in the way. From your eyes down, the ground is in the way.
Of course it is. We call that curvature. You guys are calling it something else.
We call that being low off the ground. That's why when you get higher up, you also it's inconclusive either way at that point. But still, that accounts for not being able to see stuff low to the ground. And if there is a curve in the distance, why don't you see any curve left or right laterally?
Well, I don't really get I don't really get your point, Ohio, because we do have atmosphere. So
you were the one that was bringing up hypothetical questions in Riley's Hangout.
And I just answered your question. So what does that even prove?
Oh, well, it don't prove anything. It proves if the Earth was flat, we should be able to see from New York City to France if the object is large enough.
With no atmosphere.
Correct.
Okay.
But there is an atmosphere.
Can't happen.
How can you disprove
and then Nathan has brought up the wind turbines. If we look at them going over in a distance, we can look over and we see them fade out correctly. Bottom up is disappearing, and you guys call it dirty air, or correct?
Magnifying effect.
Well, no.
Okay.
That's not what we're saying. Sorry, let me just correct that. Let me just correct that. No, in this instance, no, we're not talking about dirty air. So today, and this was conceded by a guy who claims to be off science. Philip was on, and he's conceded the same thing. What you said earlier. We call that curvature. Well, yeah, we know it's been labelled the obstruction, formerly known as curvature. And a guy of a scientific background has come on and conceded this and said, yeah, low to the ground, you have a zone of invisibility admirably described by Arev a moment ago. In terms of what you see from the 90 degrees looking out, what you get in your Theodolite as the crosshairs, when you look down from that point, there is a limitation on what you can see, so the vanishing point is very, very short. Whereas when you look up from that 90 degree point, above the target on a Theodolite, then you've got, in essence, infinite distance. So if you've got your moon example over in Europe, looking at it from the States, it's nice and high. You're looking, I don't know how big the moon is, this is a bullshit example, but, in theory, yeah, you look up and you'd still see it because it's high enough to be off the ground with no atmosphere, but it doesn't really mean anything.
Right, but my point is you said if we look at the towers from left to right, we see no curvature, correct?
We never see any curvature.
Left to right.
Whatever.
Yeah, left to right is just the most apparent.
But you were saying we claim, the sphere earthers claim that there's curvature going away from us. The towers are fading away bottom up, and we call it curvature, correct?
Correct.
Okay, and then you said left to right, we see none of that. We see no curvature left to right.
Correct.
That's what you said, right?
Correct.
Okay, the distance of the wind turbines from me on the beach is how far, Ranty?
About 11
he said,
to 13
he said the
miles.
longest one was 13.5 miles.
Okay.
Sorry, could you say again? Sorry, I missed what you said, man.
Just asking the
I
distance
was wondering how far is the wind turbines from me, or from your location when you're shooting them wind turbines? How far away were they?
The wind turbines that I did a presentation on just today?
Yes.
Yes.
Yeah, the furthest one away was 13.7 miles.
Okay, that's from your observation. So if you observe left to right, it's not 13 miles from the left one to the right one. The distance isn't the same, so you wouldn't see them curving left to right.
No,
but if the curve is sufficient to hide objects,
image,
should
the horizon of the
that amount of
entire
curvature be
image
seen left to right to cover it?
Hold on,
no,
everyone's
not if
talking
it's not
over
as
each other.
far.
One at a time. Arav, you go first.
Go.
I was just saying, if it's a sufficient curvature to hide a boat, to hide a windmill, why don't you see that curvature left to right with a curve that crests at that hidden object and curves down from that point left to right? This isn't seen.
Okay,
Can I just get Ranty to just bring it up one more time? So Ranty, if you can just bring up those two images. So you've got the one where they're right in front of each other, and then the one where they're side on. If you can just bring those out, and then I'm going to round out the show.
Okay, let me see if I can find him.
I'd like to say about Philip. He's one of the most honest, like ball believers.
Hold on a second. Sorry, I'm trying to round my show out. So if you can just go to the one where they're all in front of each other, Ranty, far left on your tabs, I think.
There we go.
No, when they're in front of each other. This is the next one I'm going to get you to bring up, though. So here we go. So I don't know if you can see this. They lie Ohio perfectly.
Yes, I can.
Right. So what we've got is these wind turbines disappearing from the bottom up. Yeah.
Right.
Right. Going around a curve. Right.
Correct.
No, wrong. Because when you go to the next image, we have a massive problem. That massive problem is that they're not built on a curve. They are absolutely, unequivocally on a flat plane. Even though they seem, and you all ask us to account for, well, why is the wind turbine dropping behind the other one? Well, that's just a simple effect of perspective. But fact, these turbines aren't built on any curve. There's no curve to them. So all you can be seeing is the effects of perspective. That's all it is. Because they're not built on a curve. This is what you get. They're flat.
The wind turbines are all at the same distance pretty much from each other, into the distance and to the sides, right? So if they are supposedly curving into the distance, then they should also be curving to the sides at the same rate.
Exactly. So they should be curving from left to right if, when you're looking front on, they're curving away from you. If they're on a curve, they're on a curve. And as you can see, plainly and obviously, there is no curve. And with that, I'm going to say first and foremost, a huge, massive, enormous thank you to all of the live audience for tuning in and hopefully for sharing this debate. And also a massive thank you to all of the debating panel for making this debate possible. If you've not done so already, be sure to like, comment, share and subscribe. I've been Nathan Oakley and I will see you all in the next video.